So now we'll look into ideal sampling and reconstructions of low pass signals. Um, this is this we have already looked into. Like we know the concept of reconstructing using ideal impulse functions. So now if the now in the previous examples or whatever we had used for a train of impulse, this is what the symbol that we were using, but now here it is used at s of t. So when x of t and s of t are multiplied, we get the sample signal. uh, x of t here is a message signal, x s of t will be sample signal, s of t will be the sampling signal. So the whole concept is the same thing. Like we are writing the impulse train ka mathematical equation. After that we are doing the Fourier series. Now we have to find dn. To find dn, this is the formula. Okay, so this is the everything is the same as we have discussed in the previous example, previous videos for the derivation. So when you solve it, so you can denote it as s of t or delta of ds of t or whatever. So when you solve it using this way, this is where you end up with, and it will. This is a final equation that you get. Now, if I and the same thing again, we have to write ms of t is equal to m of t into delta of ts of t into t. Now m of t, and in place of delta ts of t I'm substituting for delta ts of t. After that, when I solve, this is what I get. Now when I multiply it and I solve, this is what I get. This is the same thing that we had done, so that is why I'm not uh, explaining it, but it's obvious from this. So this will be the, if in the we know that multiplication in the time domain will be convolution in the, excuse me, frequency domain. And if this is a message signal, this is what you get after sampling. This is how you should be getting it for the uh, Nyquist rate, or sorry, not for the Nyquist rate, for the sampling theorem, which is fs will be greater than or equal to 2f1. This case is for fs greater than 2f1 because there is no touching, touching. And then when we use a filter, low pass filter, this is what we can extract. So we are basically extracting the signal. And to do that, so if this is our signal, we are using a filter, and we will get our original signal. So m of f will be what? Ms of f into hr of f. So if I do the Fourier transform, this is actual convolution, sorry. When you convolve it, it's convolution. Now when we convolve it, and when we convert it into time domain, it will be multiplication. So f inverse indicates we are doing Fourier transform here. So m of f will become m of t, and this whole term we are doing the Fourier transform. When we do that, it will become sorry, this was multiplication itself. It will become convolution. So now hr of t can be written as this. Uh, since it is a filter which is which whose bandwidth goes from minus b to b, that is why we have used b here. We are integrating over minus b to b. It is hr of f. This is the Fourier transform. This is hr of t, hr of f. we need hr of t, right, to find, but we know hr of f, we don't know what is hr of t. To find hr of t, we have to do the Fourier transform again. So hr, this is the formula for Fourier transform. Now let the height of this filter be k. Okay, height means, I mean, amplitude be k. So in place of hr of f, I'll substitute for k, and this comes here. And when I solve for it from, and I integrate it from minus b to plus b, this is what I get. So after getting this, I know from Euler's rule that e power j theta minus e power j theta by 2j is sine theta. Okay, so using 2j here, and this is our theta basically. So this is what we get. But we also know that when sine theta by theta is sinc function, sine theta by theta is a sinc function. So we are multiplying it and dividing it by 2b, so that we get the whole term here. And so this term will be sinc function. And so this is how it's written. Okay. Now when we come back to, we found hr of t right now, but we know that we need m of t, right? So we know that m of t is hr of t convolution ms of t. Now in place of hr of t, whatever form we got, we are going to write it here, and we are convolving it with ms of t. So I'm writing it right here. So when I multiply or I convolve a sinc function with impulse, this is what I'll get. This is the rule, that this is what happens. So the convolution goes away, and in place of t, I'll get t minus k ts. So this is the reconstruction of an message signal using low pass filter. So I'll just briefly go briefly revise what and all it was. So we need a low pass filter. Okay, everything is same, the derivation is same. We know that the impulse train or drain, this is what the impulse train equation is. Now we know that it is periodic, and since we are, and so we are applying Fourier series, and after applying Fourier series, this is the formula that we get. Now we need to find what is dn. So to find dn, this is the formula that is there for dn. Now after solving for it, now this is the equation that we get. And after getting the equation, we know that this is the equation you have to always remember, because this is a reconstruction of the message, the sample message signal ka equation. So now we have to substitute for delta of t, ds of t, whatever that you have got. And after substituting for that, this is what we will end up with. And then you just have to, you get the equation for ms of t. Now we know that ms of t is m of t into s of t, and when you convert it into frequency domain, it will be convolution. Now how do you solve for convolution? Now after solving for convolution, uh, you have to find, using low pass signal, we have to extract the m of f from ms of f. To do that, we are using hr of f. So now hr of f is used to extract m of f back from ms of f. To do that, we know that m of f is multiplication of ms of f and hr of f. So I'm taking Fourier transform of that. After taking Fourier transform, multiplication becomes convolution. So that's the rule. Multiplication always becomes convolution after Fourier transform. So now I have hr of t, but I don't know what hr of t is. I have to bring it in this form. So what I'll do is I'll apply the Fourier transform formula. This is the Fourier transform formula, and after applying, I'll solve it using integration. And after solving, this is what I'll get. And using Euler's form, I'll write it in sine function form. And after that, I'll write it in sinc function. And this is what I'll get for hr of t. Now after getting that, I'm just substituting it back into HR of t into convolution ms of t, and when I substitute for HR of t, which I got it as 2bts saying 2 pi bt and ms of t, when I convolve both of this, when sync function is convolved with impulse function, this is what I get. Okay, so that's the end. Thank you.